Welcome back. It's that point in the course where I have to remind myself about the famous saying, don't let the perfect become the enemy of the good. There's always a temptation to go back and retake bits of lecture because they don't quite meet your high standards in recording them, even obsessing over little things like, I called omega gamma by mistake because I was in the middle of a piece of maths. So I'll retake all the big things that I mess up, and some of you will have seen cuts in some of my past videos where it's pretty obvious I've had to make a little chop and fix something up. But all the little things, I'm going to let them wash over me and just apologise and let them go. Okay. I might put comments if they're really big and worthwhile. Today's background, anyone who's been to Japan will know it. It's Nara in middle country of Japan. I first went there in 2000, and there was the odd deer wandering around here or there near the temple, so it was kind of really nice to see some wildlife out and about. And I went back last year, and it was literally mind-blowing the number of deer that are in Nara now. And it's gone from nice to it's almost amusing to watch how much of a menace they are. They're standing in the middle of the streets, or they're blocking some shop front, or they're wandering up and trying to steal some tourist's handbag. And it's sort of amusing at the moment to realise that I've got a bullet on my slide. Nothing implied there, but maybe venison will be the next local delicacy in some parts, once they have to bring the population of deer back under control and their bad behaviour. Sometimes they're really nice. Okay, so that brings us pretty roundly onto Coriolis Force, and I want to spend this half dealing entirely just with Coriolis Force, get it out of the way, and we can move on to other things in later lectures. So, Coriolis Force, new term that showed up. It's one thing that you probably haven't seen very much of in physics so far. And it's another inertial force that arises from a body that's actually moving with respect to a rotating reference frame. Okay, so you can see in this term up here, there's an r dot cross omega, which basically translates into a v. Okay, the Coriolis force is usually very small, and it's usually very small, at least on Earth, because the rotation angular velocity of our Earth's rotation is quite small, okay? And so you can put some numbers to this. The angular rotation for the Earth is about 7.3 by 10 to the minus 5 radians per second, and you can get the acceleration out here by taking the maximal cross product, so it comes out as 2v omega. And so what you find is, for an object traveling at 50 meters per second, like a baseball, your acceleration is actually quite small. It's 0.007 meters per second, and literally no perceptible effect. You can work out, do it as a little Fermi problem. You throw the ball at this speed, how far away is the pitcher from the batter in baseball? How much difference does that acceleration make at most to where the ball goes? And you'll find that's a really tiny quantity, right? You get that out pretty quickly. And then you can come up to something like a bullet. So, if you've got a rifle, typical muzzle velocity is somewhere in the order of high 900s meters per second. And over short distances, you won't notice it, but if you're on a long range shoot, you're shooting, 1,000 yards or so, it's good for about 3 or 4 inches over 1,000 yards. With even quite small accelerations, okay? And again, that's another Fermi problem you can do for yourself, okay? So if the velocity is high and the distance is long, or it acts over a significant amount of time on Earth, you will actually see Coriolis force. And this is, to give another example, is weather systems. So low pressure systems rotate one way in the northern hemisphere and the opposite direction in the southern hemisphere. And of course, that is a Coriolis effect because you're acting over a very long distance with reasonable velocities, wind speeds fairly high in these systems, especially in the upper atmosphere, and acting over long time scales of order days, right? And so you see this effect. And then there's the classic myth of the toilet water rotating the wrong way in the southern and northern hemispheres. And there's 2 reasons why that's wrong. One is that you're now dealing with velocities of sub-meter per second in a very small space in a very small amount of time, so your Coriolis term is going to be negligible. The other thing is that the toilet design between the northern hemisphere and the southern hemisphere differs quite radically, and so while you might go to the United States, for example, and see a toilet that tends to swirl, which, you know, places like The Simpsons get made, that's where they have, come down to the southern hemisphere and it tends to be more like a dumping wave than a swirl, and so the experiment's practically undoable, okay? And not worth doing, because anyone who knows their numbers knows that it's not going to matter at all, okay? So that's magnitude. And magnitude is pretty easy with Coriolis force. The tricky thing with Coriolis force is direction, okay? And what happens is that the force always acts perpendicular to the velocity of the moving object with a direction given by the right-hand rule. If we just pop back for a second, you'll see that will come out of this cross product. There's one way to do this, which is always to keep it mathematical, right? So you have the R first and the other terms following. And again, this is a convention I talked about in yesterday's lecture. For all of the rotational problems, you just default to putting R first, with the exception of the angular momentum vector itself when you do that, okay? The other thing, and that, you know, mathematically brings it out, but often you're having to deal with it as a what would my direction be, and then you have to sort of build a mental tool for how to remember this thing, right? The nice way that I find to remember it is that it acts almost as a direct analog to the right-hand rule in magnetic field problems. And what's interesting is that the velocity term ends up on the same side of the cross product in the Coriolis force cross product and in the magnetic force cross product. So because the V is on the same side of the term and the force is the same outcome, you can use the same right-hand rule to do that. And so that brings me to one of my old first-year lecture slides, Adam's foolproof right-hand rule. And those of you who will have had me in first-year lectures will have seen this for magnetic fields. Now I'm going to co-opt it and use it for Coriolis force. And so you'll remember that thumb is a hitchhiker thing. So you go places with your thumb, so that's always your velocity. You point which way you want to go when you're hitchhiking, which I don't encourage. No one can assume I'm encouraging it, but it exists. And then your magnetic field would be along your fingers, right? And the force would come out of your palm for a positive particle if you were doing this as a magnetic field problem, right? Velocity, magnetic field, force. Here we keep the velocity with the thumb. The force is still going to be associated with palms, always is, and so our fingers now become the thing that's the other component in the equation. So now it's your angular velocity vector, and then the force for a positive mass, same as force for a positive charge, comes out of your palm. And of course, there's no such thing as a negative mass, so there's no out the back of the hand for Coriolis force, okay? And so then it's pretty easy. You just point your thumb with the direction that your thing's going, your fingers along whatever the angular momentum vector is, which, as we saw in yesterday's lecture, you can get from the corkscrew right-hand rule, and that will get you your Coriolis force out, okay? And so this is actually one of the really nice things. It's part of the reason why in first year I call it my foolproof right-hand rule, because I basically make it to work for every right-hand rule I ever get in some way, okay? And here's a good example of it. I use it for Coriolis force as well. It never fails me. Okay, so it helps also to try and make very quickly a little bit of sense of Coriolis force and what it actually is. And it sort of comes back to yesterday's lecture as well, in the sense that a lot of these rotational problems are not mathematically difficult, they're visually difficult. And so the maths often never gets any more complicated than some cross products and maybe a couple of simple DEs. And when we do Fuco Pendulum, we'll do a DE and we'll solve it the same way we've solved before, so we'll go through it fairly quickly. But the difficulty is trying to see what's going on and work out what your components sometimes need to be, which one's the sine component, which one's the cos component, and how this all fits together. And Coriolis Force is interesting to think about just from the perspective of what is actually going on in your system, okay? So let's take it from a sphere to a rotating table or a platform. Anyone who's been to, I used to get in trouble for this when I was a little kid. You go to Yum-Cha restaurant, they have like the turning thing on the bottom, and I always want to sling it around as fast as I can and watch everything go flying off. If you have one, you can sort of play with this. It's kind of fun. The other thing to do is to get your parents, in the old days, and actually maybe now because vinyl records are still a cool thing, get your parents' LP player and stick something like, you know, little Quantum Darth Vader on there, and then turn the record player on, and you can do these sorts of experiments for that. Okay, so if you're a DJ and you like to mix, you can get in there and do a few Coriolis Force experiments for yourself. Okay, so let's imagine we've got some rotating turntable, could be Yum-Cha turntable or LP player. And what we do is we put on there 3 crosses, A, B, and C, and maybe what we do is we put like 3 little observation positions on there. So it could be like a tiny little eye, could be an ant or something watching, it could be a little photodiode in the bottom, and we could do this experiment properly, okay? And then we attach, now our observer is going to rotate with that rotating platform, and then what we can do is make that fully frictionless surface, and then have something slide along that frictionless surface, okay? And so what's going to happen is, as it slides along, it's going to have initially had its kick radially, and it's going to want to travel in a straight line, and it's frictionless, so there's not going to be any coupling between the two. So it's going to travel in a straight line, and this thing's going to continue rotating. And so if I do that, you can try this for yourself as well. Take an object, and then it's just going to go forward like that. And if I do that while I'm turning around, what it looks like actually, from my perspective, is that this ball is actually doing this, right? And you can see this here as seen in this rotating reference frame, right? So it would head out to there, to there. And if I consider it from my fixed inertial frame, this object's going out that way, and what's happening is my observers are moving around, right? So as I come around, my inner one will come around a little bit to here, my next one will come around a little bit to here, my next one here will come around a little bit to here, and so forth, okay? So what's really going on is that you've just got a linear motion relative to a rotating reference frame, and that is then generating you what appears to be a force, right? If you look at it from your rotating reference frame, it looks like there's a force acting on this thing because you said go forwards and something has made it turn around a corner, okay? And this is why we sometimes call these fictitious forces, because there's not actually a real force acting on this thing. There's an apparent force acting on this thing simply because of the fact that you're dealing with a non-inertial reference frame, okay? And the one thing just to point out here is that you can think about Coriolis Force in this way for just about every Coriolis problem, okay? So if you take sort of your shooting gun over 1,000-yard range, what's really happening there is once the bullet leaves the gun, it's got the same problem that I was talking about in the skydiver in the first half of the lecture. It's now no longer mechanically coupled to the Earth, so it's been set off on its initial motion. And then the Earth continues rotating while this thing is moving along. And eventually because the Earth is rotating, but you're the observer on the Earth and the target is fixed to the Earth, what will happen is it will move relative to the target and hit the target in the wrong position. And that's why you might have like a 4-inch correction on your sighting over 1K, depending which direction you're facing. And it depends which direction you're facing, right? If you're shooting to the west or you're shooting to the east, you'll get a different offset due to your Coriolis force because of the right-hand rule. And you have to correct for that if you're doing very long rifle range shoots, okay? So this brings me back to my example from earlier of skydiver jumping out of a plane, okay? And I'll put some notes on the forum site about some of the complexities of this problem, because otherwise the lecture is going to blow out to massive lengths. But what we have here now is the question of how does the Coriolis force due to the Earth's rotation affect their free fall under gravity, okay? And so what we're going to do here is come back to our earlier problem, which looked like this. And all I've done here is written fgrav as mg0, okay, from using my earlier result. And we're going to add on our Coriolis force, okay, as a correction. And so this is probably a good point to talk explicitly about corrections, because this is one of these things that sort of sneaks up on you as you do your physics degree. You start to hear your lecturers talking about corrections and zeroth order corrections and first order corrections and and we're going to do one of these in this problem actually. And so what you can see us doing in this lecture whole up is we start with just ignoring the fact that the Earth rotates. And we have our true gravitational force, right? And then what we do, or what we did in the first half, was we made a correction to that force due to gravity to account for centrifugal force due to rotation, right? So you assume that the Earth is rotating, the skydiver is rotating with it, okay? And there's a centrifugal force that counteracts gravity in that particular situation. And that would be like a centrifugal correction to the problem. And so now what we're going to come through is add a Coriolis correction, so to speak. So we're going to make another adjustment to what that would be, accounting for that extra force. And often we do this quite a lot in physics. We take the simplest case and deal with it, and then realize that actually the problem's a little bit more complicated than that, and we need to add a smaller term on to correct that, and then a smaller term to correct that, and a smaller term to correct that. So you can imagine, you know, we might put another correction on later on that accounts for the fact that the angular velocity of the Earth is very, very, very slowly changing, and that will add another term on and try to get more and more progressively accurate answers as we work our way through, okay? And this is often handling imperfections of the problem, and this problem is a little bit imperfect as well, so I'll talk about that in the forum separately. Okay, so we can write this thing as what we had before plus an additional term, and that enables us to actually go back to what we had earlier on, right? So we could write this as mg plus f Coriolis if we wanted to, where we're just adding a new correction to our already corrected term, okay? We can pull the mass off, so let's call this r double dot is g plus 2r dot cross omega, and we can call this equation 1, okay? So this is our new acceleration in our reference frame, adding a correction on for Coriolis force, okay? There's one nice feature of this equation, and it's that it has terms in r double dot and r dot, but it doesn't have any terms in r. And because it doesn't have any terms in r, it means we can take that equation and apply it anywhere we want and we would have the same equation, right? It's not positional dependence. In a sense, this is the same thing as translational invariance that I talked about 2 lectures ago. And what that means is we can change our coordinate system and our origin, okay? And so we do exactly that in this problem. We shift our origin to where our problem is, so our skydiver. And what we do is set them up a coordinate system where we have y pointing north, x pointing east, and z pointing up. Okay, so it's now a Cartesian coordinate system. Y would be north, x would be east, Z would be upwards for where I'm sitting at the moment, okay? And that equation will hold exactly the same in that new coordinate system without any problems at all, okay? So then the step is now to work out the components of the various terms in this equation in that new coordinate system that we have. So R dot is really easy. Sorry, R single dot. It's just going to be x dot, y dot, z dot. Breaking that up into components. And then omega in here, I'll let you convince yourself of exactly what the various terms are in here. But the x term is 0. The y term is omega sine theta, and the z term is omega cos theta. Okay, good little composition exercise for you to do to separate that out. So the first thing we need to do here is get the cross product, r dot cross omega, right? R dot cross omega. And this is the one part in the course where knowing how to do cross products quickly and effectively is really important, okay? And I always like to do them with a sort of a determinant method. So I, j, k, put your first vector on the second row, sorry, and then put your second vector on the bottom row. So this would be 0, omega sine theta, omega cos theta. And then the way this thing decomposes is as pairs, right? So you go top left, the cross in the corner, and it's those two minus these two, okay? So it's working from here, it's those two minus the product of these two, okay? So that first term will be y dot omega cos theta minus z dot omega sine theta as the first one. The one in the middle, the way I always remember it is that you reverse the cross, okay? So you have this one here, and now let me change the color just so we got some clarity here. It's this, it's the other opposite two pairs, and it goes, you do the other way. So it'd be this one here minus this product on the other side, okay? I always find it easier to remember geometries over minus signs, but if you're one of those people who remembers minus signs, you can do it that way as well. So this will now be z dot times 0 is 0 minus x dot omega cos theta, and then the z term is the k on the other side, and it works out the normal way. So we end up with x dot omega sine theta as our z component, okay? Make sure you're practiced at doing that. You should be able to do it fairly fast, and like most things as an undergraduate, the trick is to work out the things you need to do regularly and work out how to become really fast at them. Finding components, doing cross products, doing dot products. The faster you get at the little skills like that, the easier your traffic is in exams. So we can now split this into this equation that we have above here, number 1, into 3 pieces, right? We've got x double dot is equal to 2 omega y dot cos theta minus z dot sine theta. Y double dot is equal to minus 2 omega x dot cos theta, and z double dot is equal to minus g plus 2 omega x dot sine theta, like so, okay? All right, and so all I've really done here is take this equation up the top. All of the terms have a component due to this, and then only the z term has a component due to the g, which I've brought down into that term down below, okay? So this is kind of still our equation 1, now just broken into components in my new coordinate system. And you'll notice that that also has no terms in x, y, and z, so it's not positionally dependent either, okay? Now there's a slight positional dependence to it tied to theta in some senses, right? But not inside the implicit coordinate system that we have. And that hasn't changed from when we first set up the problem, that theta was still there as well, okay? So we've translated that across. Just in case any of you think, oh, hang on, what about theta in here? Okay, so we're going through and we're making corrections, right? And whenever you're doing sort of correction approaches, sometimes the easiest place to start is to just make the correction go away, right? Um, so we can start here with omega being 0, mixing up my Greek letters again. And this is kind of, if you think about it, if you took omega to the power of 0, it would be equal to 1. And so all we've really done is just taken the equation without a omega contribution to it, right? And so this is why we call this the zeroth order correction. There used to be, when I was a kid, a non-alcoholic version of whiskey sold in the supermarkets called Clayton's, and the motto for it used to be something like the drink you have when you're not having a drink. And the zeroth order of the correction is sort of the correction you make when you're not making a correction, right? And often you do this just to get a starting position for your problem. So if we do this, if we come back up here and we basically make our omega 0 in the thing above, what we would have is x double dot is 0, y double dot is 0, and z double dot is minus g. And that makes perfect sense in terms of our skydiver, right? As soon as you jump out of the plane, your acceleration in x is nothing, your acceleration in y is nothing, your acceleration in z is g downwards, rapidly accelerating you towards the Earth, right? So we've got this, and let's just integrate this up and see where it goes, right? So we can integrate, and so this will give us x dot, and this would be a constant, and we can make it 0. Y dot is also a constant, and again we can make that 0. And then z dot is equal to minus gt, and we could add a constant in here, but let's for the moment not, and we'll call it 0. Okay, and you've gone, hang on, he's called all these constant zeros, what's going on? The first two, x dot and y dot, I can make that constant 0 because my acceleration is 0, and I had no initial velocity in the x or y direction, right? So I'm going to say that's 0 in this particular case and propagate that down through the problem. If I recast this problem of, I'm moving at some x dot in this particular case, then I'd have to include that as I work my way through, okay? And so again, this is one of these things of being an imperfect problem, because when you jump out of a plane, the plane's moving, so obviously you're moving with it, and so the assumption that you're just falling directly from free fall without that is not quite perfect, but you can propagate it through the problem and find that it just adds a little bit of complication to it. Okay. And then again, z dot, that constant on the end would be any initial velocity up or down, and that's why we can treat that as 0 as well. We can integrate this again, and so this would give us x is equal to a constant, and I'm going to make that one 0, and y is equal to a constant, and I'm going to make that one 0 as well. And that one's simply because I'm going to assume that I'm dropping directly above the origin of my coordinate system, right? So really it would be the starting position. If I was 1 mile away from where my origin for my coordinate system is, then there would be numbers in there and I'd have to put them in, okay? And then z here is going to be minus a half gt squared. And there will be a constant here, and that constant will be the initial position that we had. So it will be our height, right? And again, this is a perfectly rational approach to dealing with Newton's equations for just this skydiving example that we've got in here, right? So we've just popped out all the things that you'll know about from dealing with just falling under gravity in your first year courses. Okay, nothing special, right? We can call this set of equations 2. It's kind of our starting position. We're back to something that's not very useful. But what we can do here is use that as a position to get our first order correction for this, where we keep our omega, right? So what we can do is take what we know from 2 and use it in 1. And what I mean by that is, if I just scroll back down for a second, This term here, y dot, I can use that y dot. This term here, z dot, I can use this z dot. And this term here, x dot, where it appears in both cases, I can use that x dot, and so forth, right? So what I'm doing is saying, okay, now I'm going to use equation 1 to correct my starting position, which I've got as equation 2, okay? All right, so what happens when we do this? Our x, wrong color, our x double dot will become 2 omega. Our y dot is 0, so it goes away, and our z dot is minus gt with a minus, so it will be gt sine theta. And I could get rid of the brackets there if I really wanted to anyway. Y double dot will now be, if I put my x dot is 0 into that equation, it will be 0. And then my z double dot in here will be my x dot is 0, so I really just get back my g. Okay? And so if you consider what's happened here, our starting position before was 0, 0 minus g. And now, once we apply our Coriolis correction to this, we've got a term in x double dot, 0, and minus g, okay? And so our first order correction here is simply that we now have an acceleration pointing along x, which is to the east, okay? And that kind of makes sense because the Earth is rotating on its axis that runs, you know, roughly from north to south. And you all know there's complexities about magnetic poles and rotational poles and all this sort of stuff. So depending how we define north, is running east, and we rotate along that east-west direction, and so we get where our motion is in this direction. So if you think about Coriolis force, we should end up with a component in this easterly direction popping up in here, okay? So we can come in here and integrate this thing. So our x double dot is 2 omega gt sine theta. Our, wrong color again, our x dot is then omega gt squared sine theta, okay? And so there would be a half there that's cancelled the 2. I can add a constant to that, but the same as my logic earlier, my constant I'm going to add is 0 because I've got no initial velocity. My x is going to be the next integral for this, so omega over 3 gt cubed, getting tired, write 3 correctly, sine theta. And now you'll notice that we're to sort of a first power, because omega is basically just omega to the power of 1, right? So this is like a first order correction. And you can imagine we could use this to feed back around and feed back around and feed back around to get higher order corrections, but we've pretty much exhausted everything we need for this problem to keep on going, okay? And so now we're at a point where we can actually work out an answer to this, which is that there will be a deflection in the x direction, and that deflection will turn into, you know, missing your target. So you can imagine you've gone up very high and you drop this thing out of a plane or a helicopter, so you don't have to have x and y components of velocity, because a helicopter can stand still, and you want to drop it directly onto a target right down below and hit that target. How inaccurate will you be because of your Coriolis force in this particular case, okay? So let's imagine we're dropping like an object and it's going down by, let's make it only 100 meters just to keep it nice and simple, okay? So we're sort of abandoning our skydiver problem here for something that's a little simpler, like a rock falling 100 meters, okay? So we're going to start at z equals 0 for the moment. Let's just think about this as resetting our coordinate system so that our height z is where we start and we fall by minus h, just because it makes life a little easier to calculate. What we'll have is that z is equal to minus a half gt squared at the end, and the end will be a height minus h, right, below that starting position. So minus h is equal to minus a half gt squared. T squared here is, don't need the square root yet, 2h on g. T then here is square root 2h on g. Okay? Fairly simple Newtonian mechanics problem, and you could do it another way and get the same answer out. The main reason why I set z equals 0 to start with is I don't want any additive terms to have to clean up here. That makes it kind of difficult. I'll let you play around with this one for yourself a little bit. Okay, so now we can work out our deflection as we go as we fall downwards here, and it will be omega over 3 gt cubed sine theta. And of course, we've just got our t because we know how long it takes to fall through a height h. And we need to choose a theta. So let's just make it 90 degrees. Let's do it at the equator, right? Because it's obviously going to maximize sine theta here. So this will be 1/3 times omega g times 2h on g to the 3 halves, okay, because we've got a square root that we're cubing, times the sine of 90 degrees. And you can put in 100 meters here. This guy here will be 10 meters per second squared. Same with the g up the front there. And then our omega we know is 7.3 by 10 to the minus 5 radians per second. Put all this together and it's about 2.2 centimeters, right? So if you take an object and you drop it a distance of 100 meters, or you have a skydive and they come down by 100 meters, base jumper maybe, that's 100 meters is not far for a skydiver. Its deflection due to Coriolis force in that easterly direction will be basically 2.2 centimeters. Okay, and this basically comes about because the Earth's rotating while they're falling, and so where they thought they were falling to, they've fallen to a very slightly different position in this problem. Okay, nice little problem. Highlights how small Coriolis force could be, and if you wanted to, you could work out the equivalent correction for the centrifugal force due to that deflection, and you'll find out that in a similar way, you've got small magnitudes there that are very tiny corrections to your problem. Okay, but sometimes they're important. If you can measure something to 1 part in 10 to the 9, these things matter. All right, that brings me to the last piece I want to do in here, which is the Foucault pendulum. And it's one of these classical Coriolis force problems. You kind of have to do it. You can't not do it in Coriolis force. And what we have is, some of you have seen one. There's one floating around in a lot of physics departments and museums around the world. You have a very, very, very long string connected to a very, very heavy mass pendulum. So usually this is like some piece of high tension wire. And often, sadly, one of the things that goes wrong with Foucault pendulums is that the cable actually snaps, because what you want to do is make the mass as big as you can get over a bigger distance as you can get, and that means you've got some fairly big forces acting on this, and they often don't last very long unless you design them really well. And so what you have is your pendulum swinging backwards and forth, connected only to this pivot point, and you want it to execute very small oscillation down here so that you can take this limit of the angle sine theta that it makes being roughly equal to theta, and you let this thing swing and the Earth rotates underneath it, and so what you see instead is basically the angle that this thing swings through changes as a function of time. I've got a video I'll show it right at the end, okay, just so you can see the real effect. Many people have seen a Foucault pendulum. Not many people have seen the outcome of it, and even fewer have seen the outcome of it in real life, because one of the tricky things to do is actually to make sure that someone doesn't muck around with it over the number of hours you need to accumulate in order to see the effect, right? Be a great undergraduate lab experiment if labs went for 8 hours, which most of you would think to be cruel and unusual punishment. All right. So what we're going to do here is now write our force equation as usual. And so we've got mr double dot is equal to, we've got our tension force, we've got our mass due to gravity, and we're going to go back to our pure gravity term here, and then add all of the other corrections that we'll be dealing with in today on top. Okay, so this will be plus m omega cross r cross omega plus 2m r dot cross omega, like so. Okay, and which way you order them and put minus signs in shouldn't make any difference to the answers, but just be careful which one you choose from which book, because it's easy to confuse yourself if you take different parts of different things and then bolt them together without thinking about it. Okay, so this thing is going to be t plus mg. So really what we're doing is just burying the centrifugal term in here, because we don't care much about the centrifugal term for our Foucault pendulum. Okay, plus 2mr dot cross omega. Okay, so I'm really trying to do something here in the maths where I expose the Coriolis term, because that's the thing I'm interested in as the driving effect. Okay, I'm not going to draw the diagram again. It's in my notes as well. Here's what the situation looks like. So you've got mass hanging off down here. This angle beta here is very, very tiny. So much so that we can basically treat it as not being trig. And we can also assume that our tension force predominantly acts vertically, right? So what we can do in here is if beta is small, we can say that our z component of the tension is t cos beta by trig. And of course, if that's really small, cos beta goes to 1. So really, the z force of our z component of our tension force is almost entirely the tension force. Okay, and so we can say that this thing is basically just mg. We also need to think about the x and y components in this problem, and what we can do here is basically rely on the fact that the force decomposition here and the positional relationships here between x and y can be pulled out based on sort of a similar triangle thing in here. So the relationship between t of x and t will be identical in terms of a triangle to the relationship between x and L. You could do this with trig as well if you want, and it takes a few more steps to pull this out, but you can just do this as a similar triangles thing, right? So we can write a relationship here that goes tx on t is equal to minus x on L, okay? And quick pointer on exams here, this is why it's handy to know multiple ways to get the same thing, because sometimes you just go, well, there's a quick way to do this and I'll do it this way. And that's the thing that gets you the extra time you need to do better in other parts of the exam. Okay, so again, it's a good lesson to do lots of problems. Ty on t is equal to minus y on L, okay? And also be good with your general technique. Too many people study right before their study period and they try to study the material that's in the course and forget about studying the underpinning problem solving. And in my exam study periods, I used to keep like a day or two just to remind myself of all the tricks that you'd use for problem solving and then focus them on a specific course. Okay, so Tx is equal to minus mgx on L. Ty here is equal to minus mgy on L. And the x and y components of g are 0 here. And so we can break this thing down into components. And we don't really care about the z direction here because we're looking at our oscillation. So we can just wipe that out straight up. And z dot's always small. There's a few things that we know in here. So x double dot is going to be minus g x on L. Okay, I've just pulled out the mass. Plus 2y dot omega cos theta minus 2z dot omega sine theta, okay? And these two terms that I just put on the end came out of the problem we just did, right? So we've got this same implicit idea that we're translating our coordinate system up to where we're interested in and working everything out, and we've got an omega vector that's broken into components like we had in the last problem. Okay, so this is minus gy on L, minus 2x dot omega cos theta. And we're not going to care about the z term in here, z double dot, because it's not very interesting to us in terms of what the motion in x and y is, which is what where the interesting part of this problem comes about. And we also know that z dot is always going to be small, and it's always going to be small because our pendulum has constrained motion, and where it's constrained, you know, essentially to the circle of length L, and it's over a very small angle. So our change in z is going to be small, so z dot is very small, okay? So what we can do straight up here is take this term and say that it is going to be 0 for beta small, okay? And what that means now is we've got two equations that look kind of similar, and we also know in here that omega naught is square root g on L for beta small, right? If you take a pendulum that's oscillating over a very small angle, you know that the angular frequency for that is just g over square root g over L, okay? First year result. So we can pull that in, and what we can write here is that x double dot minus 2 gamma z y dot plus omega naught squared x is equal to 0. So let me just define something up here. I'm going to call omega z omega cos theta, and to make that clear, if I go right back up to the problem I just did before, you can see it right here, okay? So I'm basically just saying that that's the z component of omega in this particular case. And then my corresponding equation here is y double dot plus 2 omega z x dot plus omega naught squared y is equal to 0. Okay, and we'll call these 1 and 2 for now, right? What do we have here? We have a problem we've solved before, and I'm also going to tell you that this is not the last time you're going to see it in, you know, the next series of lectures I'm doing, because I remember writing it up again the other day. So one thing to put in your minds, this is a really common DE to see in classical mechanics, okay? And I'm going to go through the solution a little faster this time because I did it way back when I was doing oscillators, and you can go back there and have a look at it in really good detail. So let's do it quickly. The way you handle this, you've got two coupled DEs, and so we can come up with a eta function here that is basically x plus I y. Okay, so we basically take these coupled equations and turn them into a complex plane. Okay, so what we need to do now is turn our two coupled equations into one equation on its own. And the way we're going to do that is we're going to take equation 2, multiply it by I, and add it to equation 1. Like so, okay? And so it will give us I y double dot plus 2 omega z I x plus omega naught squared I y plus x double dot minus 2 omega z y dot plus omega naught squared x equals 0. And we can now write this in terms of eta, and I'll let you verify this for yourself. It's eta double dot plus 2I omega z eta plus omega naught squared eta equals 0, okay? And so now we have one unknown, which is a complex number eta, and one DE to solve, and it's a very classic DE. We know what the solution to this thing looks like. We basically write eta of t equals e minus I alpha t. So we take our usual trial solution approach here with an I on the top, because we'll see that that comes out quite necessarily. Okay, so we can substitute that into our equation up above, right? So d squared on dt squared e minus I alpha t plus 2I omega z, that should be a dot just there. Is that right? Yes, it is. I left it out. Yeah, because that's an x dot there, that's a y dot there, that'll give me an eta dot there, and that will mean that there's a d on dt just here. Okay, good. E minus I alpha t plus omega naught squared e minus I alpha t equals 0. And of course, what we do here is we execute our two derivatives in here and then collect all of the exponential terms off to one side. Okay, I'm going to skip this step to keep the lecture from blowing out too badly. Minus alpha squared probably has blown out pretty badly already. 2 omega z alpha plus omega naught squared. Okay, e minus I alpha t equals 0. Okay, I've always got this competition between trying to keep inside reasonable amounts of time and actually do problems properly, so that I'm not skipping heaps of steps and people are getting confused. Okay, so we've solved this sort of problem before as well. We know that this exponential only goes to 0 in not very useful places, and so what we want to do is make this term go to 0 to pop out our solutions, and it's a quadratic that we can solve. Okay, so this quadratic, real quick, is 2 omega z plus or minus the square root of 4 omega z squared minus 4 by 1 by minus omega naught squared. Okay, when I tend to write solutions to quadratics, I tend to write down all the terms and then work them out, rather than try to skip steps, just to avoid making bad errors in there. And the one thing that you'll notice is I can take this quadratic up here and apply a minus sign right through the whole thing, which will explain why I've got minuses in funny places in that solution just there. And so this thing is going to be omega z, because I can use the 2 from the bottom to clean up the 2 from the bottom to clean up the 2 here and to clean up the 4 in there, right? Because the 4 inside will pop out as a 2 in front of the square root. And this will be omega z squared plus omega naught squared just in here, okay? And there's one thing that we can realize in here, which is that omega z is the angular velocity of the Earth, and omega naught is the swing frequency of my pendulum, right? And my pendulum swings a lot faster than my Earth rotates, right? Because my pendulum will swing backwards and forwards at, you know, maybe 1 or 2 seconds in oscillation for hours and hours, and the Earth takes 24 hours to go around one rotation. So omega naught is huge compared to omega z. And so this term on the end here might as well just be omega naught, okay? And so what we end up with here, trying to change color and failing miserably, is omega z plus or minus omega naught, okay? Okay, so now we come to the place where we normally come to with solving DEs, and it's the same place we end up every time. We put in our first trial solution, we get out our characteristic equation and solve it, and then it tells us how to come up with a better trial solution. And that better trial solution is going to be something that looks like an exponential plus I omega z plus omega naught, and e to the I omega z minus omega naught up in here, okay? And this sign here doesn't really matter very much. And so, again, we know that that's got a common term in here, so we can actually write this as something that looks very specifically like e to the minus I omega z t. Let me just correct my notation here for a second. Let me put a tilde in there because it's not exactly equal to that, but I'm just pointing out what the form is going to look like. And then I need a constant in here, ei omega naught t plus c2e minus I omega naught t in here, like so, okay? And so C1 and C2 are constants, and I would solve them with boundary conditions, okay? To keep this lecture not from getting any longer than it has to be, I'm actually not going to solve for those two boundary conditions. I'm going to let you do that as an exercise, and you will have in my notes all of the maths that I do to do that, so you can work out what it is. But basically what we end up with in the end is C1 equals C2 equals A on 2, okay? Where A is sort of the amplitude of our pendulum, right? So what we do is we just basically say that our x direction becomes A, our y direction is 0 at t equals 0. That's equivalent to taking our pendulum and pulling it back to whatever amplitude you want to set in the x direction and then letting it swing, right? And we know in here that there's also a y direction that can come into play later on, okay? So if we think about this solution here a little bit, these terms that we've got up in here, we can decompose into cos and sine using Euler's theorem, right? EIx is cos x plus I sine x. So this thing up the top here, with a wee bit of algebra done, becomes A e minus I omega z t cos omega naught t, okay, as your final answer. And I'll let you work through the intermediate steps. You've got my notes to work through them, so it should be a fairly easy exercise. And so what we can do here is plot our x and y directions. So this would be x and y, and this would kind of be looking down on the pendulum from above, right? And so we start out initially with an oscillation that runs between A and minus A, backwards and forwards along this direction. And that basically corresponds to this term here on the right-hand side, right? The omega naught is very small, so that oscillation happens quite quickly compared to this term here. The exponential term with the omega z in it will basically act to rotate the oscillation. So what we'll find is after a little while we'll have an oscillation that's going like this. After a little bit longer we'll have an We'll have an oscillation that's going like this, okay? And that comes about from this term. Why don't it switch back? From this term, which omega z is much bigger than omega naught, and so it basically stays close to 1 for a long period of time before it even starts to change a little bit, right? And what it will do is it will remove a little bit from the x oscillation and add a little bit to the y oscillation and keep doing that and just progressively rotate that oscillation around, okay? You can do some maths in here and basically work out what rate that rotates around. And it rotates around at a rate that goes as omega z, which is omega cos theta. And theta is just your colatitude, right? So if you're at the North Pole, where theta is equal to 0, then cos of 0 is 1. So basically your Foucault pendulum will rotate around in this direction here, and it will take 1 whole day to get all the way round, okay? So basically your period of going round that is equal to 1 day at the poles. And then as you come down off the poles, you get a different situation coming out of this thing, okay? So if you think about Sydney, Sydney is at a latitude of about minus 33 degrees, And so your theta is 123.86 degrees, and so your omega z ends up being minus 0.557 omega. So it's some fraction of 24 hours, maybe half, so 12, right, for a rotation in there. And it works out to basically be about 200 degrees a day in the direction opposite to the North Pole, because we're on the southern hemisphere, okay? And this is the one experiment I've actually never seen done. What would be nice would be to have a Foucault pendulum in the southern hemisphere, Foucault pendulum in the northern hemisphere, running them both with time-lapse start at the same time, and watch them rotate in opposite directions, and they'd have to be identical so that you could wipe all this out, okay? I would give you a demonstration using the Foucault pendulum that we have in the School of Physics, but while I was looking things up for it, I found in UNSW Student Life that one of the apparently cool things about UNSW is the Foucault pendulum in the physics building has been stolen 3 times. I think if I went and had a chat to Gary and Joe, who look after that pendulum, I doubt they would call it being stolen 3 times to be cool. But anyway, we used to have a really nice wooden ball on the end of it, and now we don't. And the other difficulty with Foucault pendulums, particularly the way this one's designed, if you make it accessible to people, is that they go and try to do their best Miley Cyrus impersonation, and it's often broken. Or someone sets the experiment up, and of course it takes, 200 degrees a day, so it's a number of hours before you see an effect, and someone's come along and changed the oscillation by then, and you never see it, okay? So I've only seen it in real life once, and that was when I was an honours student, and I was doing something that's rather unhealthy, which is working more or less around the clock. So doing experiments at, 3, 4, 5 o'clock in the morning. And so I went up there at midnight when no one was in the building, set the pendulum going, went back up at, 5:30 in the morning, knowing that no one had touched it. And sure enough, I could see it had turned around, okay? But if you're well set up, and well set up in the sense that you can both keep people away from it and have a time-lapse camera, you can do something that looks a little bit like this. And you'll notice that there's little dominoes that are being knocked over down in here as it works its way around. And sure enough, you can have a look, the link to the videos in the slides. You can go have a look at it yourself. It'll work its way all the way around, and it's a really nice demonstration. So it'd be cool to have 2 of these, one in the northern hemisphere, because this one's in Japan. So it's rotating in the northern hemisphere direction. It'd be nice to have an identical one in the southern hemisphere and time-lapse them at the same time and watch them go in opposite directions. That's probably maybe the next video to be done in terms of demonstrations on YouTube. Yeah, pretty much every demonstration's been done now, so it's kind of a dead market, but this is one thing that's left, and it's a hard one. So, sorry for the length on this one. Coriolis Force is always a long one to do, and I didn't really want to put half of it across another lecture. It just made more sense to do it as one big topic, which is why we're only doing 15 lectures instead of 17. And we're going to switch to rigid bodies and inertia for the next 3 lectures. I'll see you next time.